Another important concept regarding axiomatic systems is what we call a conjecture. A conjecture essentially is a proposition which is suspected to be true due to, for instance, preliminary supporting evidence or maybe resemblance to other structures that are known to be true, etc., but for which no proof or disproof has yet been found. So what does this mean? So this is a statement which we feel like it's going to be true, but it may not be. We do not know for certain. Okay, we do not have a proof for it. Therefore, we cannot treat it as a theorem. We cannot treat it as a truth. Okay, but at the same time, we do not have a counterexample, so it's not disproven. Okay. Well, one important property here is a conjecture. Essentially, since we haven't proved it, so it cannot be treated as truth. Therefore, you cannot use in proofs. This is important. Okay, it's not a theorem. A conjecture is not a theorem. We do not know for certain that to be true. Therefore, you cannot use them in proofs. Here's an example. Goldbach's conjecture. Okay, this is quite famous and have been known like 2.5 centuries. And this is due to the correspondence between German mathematicians Goldbach and Euler. Actually, Goldbach formulated this first, but this statement was given by Euler. Every even whole number greater than 2 is the sum of two prime numbers. So this essentially says, if you give me any positive integer, essentially greater than 2, okay, there are two prime numbers that when added up makes that number, okay? So this is a conjecture and we have no proof for this. This has been stated like 2.5 centuries ago. And to this day, we have no idea whether it's true or not. The only thing we were able to do was to verify it up to a certain point. Okay, so people have worked on this problem, essentially supercomputing techniques, etc. And we have verified that this conjecture holds for numbers up to 4 times 10 to the power 18. Okay, so as of this date, we know that this is to be true. However, there is no guarantee that like in 10 to the power 21, it's going to fail. We have no idea. So verification is not a proof. Okay, be careful about this. We can verify a statement for certain values of a variable it includes. However, that certainly is not a proof. Okay, be careful to make this distinction. Another very famous example is the Collatz conjecture, and also known as 3m plus 1 problem. And this was formulated by Lothar Collatz, another German mathematician. And the statement is here: start with any positive integer. If the number is even, divide by 2. If it is odd, multiply by 3 and add 1. So 3m plus 1. Then this sequence will always reach 1. Okay, that's the claim. But to this day, we have no idea whether this is true or not. And the verification up to date is up to 2 to the power 68. It's a huge number. Okay, but as I said, this is no proof. This is just a verification up to that number, and there is no guarantee that some number is not going to spoil this beyond this number. Okay, and this problem is deemed an extremely difficult problem by even modern mathematicians, the likes of Erdős, etc. And so the statement is quite simple. You can describe this to a primary school student and he can understand it, but no solution. Okay. Okay, let me give you another example. And this is the Pólya conjecture, and this is due to the Hungarian mathematician George Pólya. For any given positive integer n, the number of numbers less than n with odd number of prime factors are more than the number of numbers with even number of prime factors. Okay, so this is a little bit confusing maybe. So just assume any positive integer n, and take the numbers below n, okay, 2, 3, 4, etc. I mean, 1 is just 1. 1, 2, 3, 4, up to n, let's say, and separate them into two groups. In one group, you have the numbers whose number of prime factors are odd, and in the other one, you have the numbers with even number of prime factors. So for instance, 4 is 2 times 2. So it has an even number of prime factors. It has just 2. But 8 is 2 times 2 times 2. So it has 3 prime factors. Okay. 6, 2 times 3. It has even number of prime factors. Or 10, on the other hand, 2 times 5, it has even number of prime factors, but for instance 30, or let's say 20, 2 times 2 times 5, you have 3 odd number of prime factors. Okay, so separate these numbers into two groups, and Pólya conjectured that the ones with odd number of prime factors are going to be more than the others. Okay. Now, this was stated in 1919, and it was actually proven false in 1958. Okay, and the counterexample was estimated to be around this number, 10 to the power 361. It's an enormous number. Okay, so you see, you never know these conjectures will fail, where they are going to fail. So verification is never a proof. That is the essential idea here.